plasma. This is what I was referring to when I said this is when everything is complete.
Thank you, Alex. Can everybody hear me in the back there? Am I yelling anything? Okay. So first I'd just like to thank the organizing committee for allowing us the opportunity to talk today about rotational shear and tokamak plasmas. This work was done in collaboration with a number of individuals in the room today. In particular, I want to highlight Edmund Hycock, who did some of the simulations that I'm going to be presenting. So just for Nunu Herrera, one of our colleagues, we have the alternate title, Fusion, how to spin it.
At this point, I think it's supposed to block.
Yeah, insert nervous laughter here.
Too much theory.
So basically what we want to talk about today, first I'm going to start out by giving you some kind of motivation, tell you the problem we're trying to solve, in particular the question we're trying to answer. Then I'll talk about how rotational shear affects turbulent transport. So if we fix the mean profiles and see what effect the rotational shear has on those. Then we're going to see, Felix will talk about the implications that the properties of these turbulent transport has for the local gradients themselves, so a 0D sort of transport model. And then I'll go on to just tell you briefly how we intend to then extend this to look at self-consistent 1D radial profile evolution. So you've heard throughout the course of the day really why we want to be looking at rotational shear in tokamaks. Experimentally, we observe these internal transport barriers. We find locally steepened temperature gradients. And these are often accompanied by large mean E cross B shears and low or negative magnetic shear. So that's what's being illustrated here in this plot. This is taken from a paper by Connor et al. It's an experiment from JT60U. And we see that we have an ion ITB here. We see the ion temperature gradient is very steep in this region, and it's corresponding to a very large E cross B shear in the same region, and sort of a zero or reverse magnetic shear. So what we're going to be talking about today is whether or not it's possible, just purely with rotational shear, to see transport barriers or bifurcations in the temperature gradient without any triggering mechanisms like what Peter was talking about earlier today.
Michael, how wide is that barrier on a colloidal Lambda radius scale?
Oh, I have no idea. I'm not sure. Maybe we could estimate, I guess.
No, there's no.
Well, but we know roughly. I mean, it's 0.15 of the minor radius, and I guess the gyro radius. Well, I don't know what the colloidal gyro radius is there, but.
But the guy who wrote the paper is.
Exactly. So Jack? All right.
If
Sorry.
Rho star is 1 over 400 to pick a number.
Yeah.
Use 4, so that's up there.
Okay. Well, in terms of Rho star, so that might be, say, 40 gyro radii across, 50 gyro radii, 60 gyro radii across.
So 15 colloidal or something. Maybe.
Thank you.
Yeah, sorry. All right, so that's the question we're trying to answer. Can you get transport barrier-like phenomenon purely with rotational shear? So here's the model we're going to be using. This is workshop on gyrokinetics, so we're going to be using the gyrokinetic equation. And in particular, we're going to be including a mean flow. It's going to be the so-called high flow ordering, so we're going to be taking the equilibrium flow, or the mean flow, to be order the thermal speed in the plasma, the ion thermal speed. But as a subsidiary expansion, to simplify the problem, what we're going to be doing is considering the Mach number to be much, much less than 1. Okay? But just to be clear, this is a subsidiary expansion, so it's still much larger than the Larmor radius to the system size. And so in order to keep the effect of the mean flow shear in the equations at this point, what you have to do is you then order the gradients and the flows to be order V thermal over L. So what we're doing is we're assuming that the gradients in the flow are a little bit steeper by 1 over Mach number than the gradients in other quantities, other mean quantities. So the equation you get after that is shown here. The details aren't that important. It's the usual gyrokinetic equation one would expect, delta F gyrokinetic equation. H here is the non-Boltzmann part of the fluctuating distribution function. And the flow shear comes in 2 places here. You have flow shear entering over here. This is the term that Arthur was referring to earlier today when he was saying the part that's contained in the Maxwellian. This is the shear and the parallel flow. And then it also comes in through this temperature gradient, which I have defined here. and this is just the advection by the mean flow. So this piece, the only part that's going to contribute here is the E cross B flow shear, part of the toroidal rotation. Right? So in general, as we've seen, this is going to be a stabilizing effect. This is going to shear the turbulence, and this is going to give us a linear drive term to excite turbulence. So this is all going to be done using the nonlinear gyrokinetic code GS2. We're going to be using, it's a flux tube code, so we're using the local approximation, which means we're going to assume that this angular frequency that we have here is expanded in this way and kept terms only at linear order. We're going to be solving this in a rotating reference frame, so this term isn't going to be here. And so the critical parameter for us is the derivative of this rotation frequency with respect to the radial coordinate here. This is the flux label psi. So in the plots that I'm going to be showing you later on, the parameter that we're actually using in these plots is gamma E, this flow shearing rate, which is related to d omega d psi by this factor of psi over safety factor Q. So this is just the radial label we're using in the simulation.
When you say you're solving in a rotating frame, have you or have you not included the Coriolis force?
So we're not here. So this was the point of this subsidiary expansion. We don't have, in theory, even though we go to the reference frame where this is not going to be there, we still have some of the Coriolis drift and so forth that should be there. But they're not going to enter because we take this Mach number much less than 1 expansion. So we're only focusing on the effect of the rotational shear here. All right. So what do we see? We're going to be looking at the cyclone base case, which I'm sure most of you are familiar with. It's a widely used benchmark case that was referred to earlier in the week. And just the important geometry parameters shown here. You have the inverse aspect ratio, which is about 0.18. You have the safety factor, which describes the pitch of the local magnetic field lines of 1.4. And what I'm first going to be considering is the standard value of the magnetic shear of 0.8. But then later on, we're going to also look at the case of magnetic shear of 0 to see what the difference is. And what we see from our linear simulations is shown here. We're looking at the linear growth rate. This is the average linear growth rate. So we're averaging over the flow K period and so forth in the simulations, and versus this flow shearing parameter gamma E. And basically what I want to point out is, of course, as you increase the flow shear, linear growth rates drop. You see some features down here at lower values of gamma E. Basically what's happening here is what was described by Arthur earlier. You have some ITG drive, which is dominant here. But at some point you have a coupled ITG and a flow shear drive driven by this gradient in the parallel velocity, which I'm going to be referring to as PVG for brevity in the talk. And so that's what drives this second hump here. So this is driven by ITG, PVG coupled together. And then what we find is that as you increase the flow shear sufficiently far, in fact, the linear growth rate itself completely goes to 0. So instead of the picture that has been seen in other discharges and at lower flow shear values, this growth doesn't continue indefinitely. There is some quenching point here linearly. And so what I'm showing you here is the critical value for gamma E at which the growth rate goes to 0 as a function of the temperature gradient scaling. And you can see it satisfies roughly a linear dependence. So
Michael, how did you arrive at this conclusion, the second bullet, that it's a mixed ITG, PVG?
So unlike what Arthur was pointing out earlier, he was looking at a somewhat different case. It was very similar, but he had a higher Q, which meant that the PVG drive was larger in that case. And so we don't find, for these parameters, instability without any temperature gradient. We require some finite temperature gradient, but if you also turn off the parallel flow gradient, there's no instability here either. So it's some coupled situation where you have to have both for the instability to survive. Yeah?
Excuse me, this is a flux tube simulation result?
Flux tube simulation. Yeah.
So, in the case of high rotating case, maybe theta k or radial wave number is regarded of a function of time.
Yes.
That kind of things are used for this calculation.
Yes. So the way that the simulation works is we have a shearing periodic box, and as you say, what that does is it introduces a time dependence in the radial wave number, which we evolve in time.
So is it time average growth rate?
This is the time average growth rates.
Not the max.
Yeah, I mean, this is not the max growth rate. So I mean, yes, there's some discussion, maybe the max growth rate is the more relevant thing to look at, but in either case, what I'm really wanting to point out with these plots is that there's some value at which the growth rate, the average growth rate goes to 0. Okay.
And the max growth rate's pretty darn close to 0 there.
Yes, 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 yes.
What did you say about
Yeah.
the Boydell velocity? Is that fixed at something or fixed to 0?
The what velocity?
Boydell velocity, is that fixed to be something or fixed?
No, so this, because we're in the high flow regime, then the flow velocity is constrained to be purely toroidal, the mean flow. However, once we go above this critical value of gamma E, for which we find linear stability, you do find transient linear growth. So what we're looking at here is the heat flux versus time, normalized heat flux at the initial condition of the simulation. And we're looking at this for which value was it? It was R over LT of 8.75 from this plot, so it's this red line. And so we're looking now at the values 1, 1.2, and 1.4 in this plot. And what you see is that as you increase the flow shear, this transient growth that you have becomes sort of more violent, so that the amplification factor increases with flow shear. And this is qualitatively consistent with recent theory, a recent paper that's been submitted by Sarah Newton, who's here, Nuno Loureiro, and Steve Cowley. So they were looking at a fluid model and a slab, and they were finding the same behavior. There's an absolute value for the flow shear beyond which everything is stabilized linearly, but you get this transient growth.
That has something to do with non-normality of the linear operator, was that?
Yeah. Non-normal. Okay. So what happens when we look at the nonlinear case? Here what I'm plotting are going to be the heat fluxes normalized to the gyrobone heat flux, and the momentum fluxes normalized to the gyrobone momentum flux versus gamma E. Yeah? Is there a question? Okay. And here I'm defining what these heat fluxes are. So it's the toroidal angular momentum flux and the heat flux. And so for low values of gamma E, we see a story which is very similar to the average linear growth rates qualitatively. We see that first the heat fluxes drop. They start to come back again here at low values of R over LT before coming down and being completely quenched. However, we see that, again, once we go to flow shear values which are sufficiently large, this transient linear growth can actually drive large heat fluxes which are monotonically increasing with the flow shear. So what this means is that linearly, if you start a simulation here with very, very small amplitudes, you get no fluxes, but if you initialize to some sort of saturated turbulent state, then you find that this turbulence persists and perhaps even grows.
Why did we see any examples of that in the previous plot?
Which previous plot? This one?
That's linear.
This is all linear.
Oh.
Yeah, so this is linear transient growth.
It's called Q, but it's just...
Well, it's a linear heat flux. Okay. So pi, the momentum flux, demonstrates similar behavior as Arthur was referring to earlier. At 0 flow shear values, one finds that there's symmetry arguments which would indicate that there's going to have to be 0 momentum flux here if we have no non-diffusive terms in the equation. And this increases with gamma E until the turbulent fluctuation amplitudes have gotten sufficiently small that it also starts to decrease before this subcritical turbulence kicks back in and the momentum flux increases again.
So you're showing that the heat flux at large gamma E depends on the initial condition, at least in a kind of 0-1. You either get something or not.
Yes.
Have you guys checked that if you further change the initial condition by multiplying all those turbulent amplitudes by a factor of 5 or 10, does it change, or is there a well-defined nonlinear steady state?
From what I've seen, there's a well-defined nonlinear steady state. So I'm guessing, if I understand your question correctly, you're saying, sure, if we initialize something to 0 here, we get 0. If we initialize it to 1, maybe we get something. If we initialize it to 2, do we get something else? Is that your question? So far, when I've looked at, say, initializing to 1 and to 2, it goes to the same steady state in the end. So it's a binary sort of.
And if you initialize it further away from where it's going to get, it just takes longer, but it always,
But it goes to the
always
same
goes
place.
to the same.
Yeah.
Excuse me.
Yes.
Is the background is showing the gyrobone unit?
Yes, gyrobone. So these are quite large, of course, because we're looking at a cyclone base case, which is not particularly.
Case of ITG?
Yes, this is ITG, and this parallel velocity gradient drive from about here outwards.
And this is chi, not q. So the cyclone base case chi is 2 or something?
Okay, this is Q, not chi.
But not multiply Q therefore.
Yeah. So it's the heat flux divided by density times temperature times thermal speed times 1 over rho star squared, essentially.
I think what he's asking is the point in the red squares, I don't know if that's red, 6.9.
The black.
Oh,
Is it-
6.9, it's 60.
Yeah, that's the
Is
usual.
60 the usual value in these?
Yes. I mean, this agrees with the cyclone base case benchmark study at 0 flow shear.
Whatever those units are, they're similar to the usual units. It's all on the same scale.
Yeah, it may not be in the same units that the benchmark case was in. Yeah. So what else is there to point out here? First off, well, we simply have subcritical turbulence beyond here. It means that you have to be very careful if you're talking about using quasi-linear models to model turbulence with rotational shear, because we've at least found one regime in which you would find linear stability, but finite and possibly large heat fluxes. Also, because you have a minimum here in the heat fluxes with respect to the flow shear, it means that we have a finite optimal flow shear value for confinement. So more shear is not always necessarily a good thing. Also, the existence of this subcritical turbulence means that there's possibly hysteresis in the system. So for instance, if you were trying to get a value of gamma E of 1 and an R over LT value of 10, then if you start out with say, at this point, so you start out with no flow shear at high temperature gradient, and you try to increase the flow shear, then you're going to follow this green line, and you're going to end up at this point with large heat fluxes. But if you did the opposite sort of thing, where somehow you could start out with a large flow shear, have small temperature gradients to begin with. So for instance, if you had a temperature gradient of 7.5 to begin with, and then increase the temperature gradient at fixed flow shear here, then you never excite any linear instability, and so your flow shear is 0. Oh, the final point on this slide, because you have maximum in the momentum fluxes, it means that if you increase the momentum input, then once you increase momentum input above this maxima, then it means that now it's possible to have a bifurcation where you can jump from this point on the plot over to higher values of flow shear. Now that's a bit misleading because we're looking here at fixed values of R over LT, and of course R over LT is going to start increasing once you decrease heat fluxes further. So Felix is going to talk a bit about how you could sort of self-consistently do this when you're keeping momentum flux and heat flux fixed.
But Michael, if I would take one of the ITB we saw this morning, shown by Peter De Vries, for sure gamma E would be larger than 1. I remember that.
The what value?
Gamma E would be larger than 1, and R over T is probably 10 or above 10. So
well, so there
should be on the green line, right?
Two points. I mean, first off, I'm not necessarily saying this is what's causing ITBs. And this is also a case which is very far away from the experimental case, right? So these values, I mean, the cyclone base case is far from optimized. So as we'll see in a minute, when you change the magnetic shear value, quantitatively these values change significantly. I think that's what you're getting at.
Gamma E here is in units of CS over L.
No, it's all that R and Q.
There's an R over Q. Essentially, I mean, you can't say exactly what Mach number this corresponds to or flow shear because we don't have the Mach number in the problem anymore. But
I'm trying to compare this gamma E to the linear growth rate.
the linear growth rate.
It's normalized to be thermal over the system size with a factor of Q. So
Yeah. What? Yeah. All right. So if you also look at if we construct the turbulent Prandtl number from the fluxes that we have, we see the following. So the Prandtl number is defined as the viscosity over the thermal diffusivity, which are defined through these relations. We see that the Prandtl number for sufficiently large values of gamma E converges to a value which is largely independent of both the temperature gradient and the flow shear, and it's of order unity. So this fact, this constancy of the Prandtl number for moderate to large values of gamma E will be used later on by Felix in some of his 0D analysis. And of course, even if you quench the turbulence, all you're going to do is you're going to increase T prime a bit. And how much you're going to be able to increase T prime depends on how stiff your transport is. So we'd like to know what effect this flow shear has on the stiffness. What we're looking at here is the heat flux versus the temperature gradient. And we see this purple line corresponds to no flow shear. As you increase flow shear, we start moving this way in the plot. You increase the critical temperature gradient, and however, you increase the stiffness at the same time. which has to happen simply because you've shifted this thing this way. But in the limit where you go to very high values of R over LT and you keep gamma E fixed, then it's eventually the system's going to look like it has no flow shear at all. It's not going to feel the flow shear because R over LT is so large. So it has to converge to this line eventually, so locally the stiffness has to increase. However, as we go to larger and larger values of flow shear, out here we see that the nature of the instability that's driving the turbulence changes. You now have turbulence which is driven by flow shear, so no longer do you have quite as sensitive of a dependence of the heat flux on R over LT, because R over LT is not what's driving the mode anymore. All right, so I'm going to end here with this last couple slides on the zero magnetic shear case, which were carried out by Edmund Hycock. And qualitatively, these look pretty similar to the plots that I showed you previously for the higher magnetic shear case. You see that the heat fluxes come down, they're quenched, and then at some point it appears they come back with some subcritical turbulence. Now there's something I want to point out. First of all, outside of flow shear of 0, we find no linear instability at all anywhere in this plot. So everything here is subcritical turbulence. That's the first point. And the other difference really with the case that I was just showing is that this critical value of gamma E at which the turbulence is quenched changes quite significantly. So these are on, this is around 1.5, which corresponds to this point here. And we see that if, for instance, you consider this R over LT of 10 value, then in the case that Edmund ran, 10 is this line here. You see it completely quenches at a value of around 0.5, 0.6. Whereas for the case with higher magnetic shear, you see there's no quenching ever of the turbulence, and because the subcritical turbulence kicks in before it can be quenched. So the question now is we want to switch our perspective, and we want to stop thinking about, given some kind of temperature gradient and some kind of flow shear, what's going to happen to the fluxes. We'd rather have the inverse problem, right? In an experiment, you have fixed fluxes because you have fixed power sources, and now we want to figure out what that's going to do to the density, or to the temperature gradient and to the flow gradients. So that's what Felix is going to talk about.
I guess any questions before you take up the microphone?
Any questions about this? Yes?
I'm just curious in your last point there. I mean, can you give a sort of a simple, intuitive picture of what the zero shear case is, or how that compares with the finite shear?
Why does it change? Well, this is again something to do with, well, first off, linearly, low magnetic shear is more stable than high magnetic shear. Also, what else is there to say here? Typically, so from the theory of Newton and Cowley and Loureiro, they find that actually the critical parameter to determine when there's linear stabilization of these modes depends not only on gamma E, it really goes like gamma E over magnetic shear. And this is because it's probably too complicated for me to explain, but it basically it has to do with the speed of the crossing points of field lines. So the relevant quantity really isn't d omega d psi, it's d omega d, what? D omega dq. And so that's why you go to lower magnetic shear, and we see quenching happening at much lower values of gamma E.
And there is a critical value for that parameter. So if the shear is low, it's always above that critical value.
Well, I mean, here you've taken shear to 0, so gamma E is equal to infinity, and so...
And everything is stable.
Everything is subcritical.
Except at 0, right, but you still need a finite gamma E to stabilize, not 0 gamma E.
Yeah, that's right.
So gamma E over S hat is qualitatively correct,
no, sure,
but
it's misleading.
Going
yeah,
0.
No, that's right. So for the linear physics, it seems like it's great, but when you look at the nonlinear physics, it's not quite as great.
I think it's worth. Can you clarify? Greg just said that a finite amount of gamma E at 0 magnetic shear still leaves a linear growth rate, I think. And I think that you disagree with that?
No, it doesn't leave
I'm sorry, I don't mean linear growth rate.
Yeah, he means flux.
Non-linearly sustained growth.
Yeah.
Yeah, but the theory involving the
was linear growth
rate was a linear theory.
Yeah, that's right. I'm just clarifying.
Arthur?
As I understand, the interpretation of the linear growth rate with the shearing is a little difficult because it's going up, and so you build the average or you take the maximum.
Yeah, so I mean, I was looking at the average here,
Right.
but when I was going to higher flow shear values, I mean, the difference between the average and the maximum was decreasing.
All right. Right, so everything goes below
Because
zero.
it goes more high frequency, but the amplitude difference becomes much smaller.
What I find maybe interesting to try, because if it's really subcritical, and maybe you could have a nonlinear simulation at different amplitudes. Is there a nonlinear simulation if the amplitude of the turbulence is below a certain threshold, it indeed decays away when the amplitude is above a certain threshold? It really takes off.
No, you're right. It would be interesting to look at the initial amplitude dependence. I mean, like I said, it's a binary thing, but where is that binary cutoff is what you're saying. At what value of the initial amplitude does it flip over to the turbulent regime versus the decaying regime?
Region also from this interpretation of the growth.
Yeah, that's a good point.
Well, intuitively, it must be something around where it wants to saturate at.
Well,
Well, it depends. If you had very violent transient growth, right, the amplification factor could
Well,
be
it has
quite
to go
large.
nonlinear, right? Basically.
Yes, but
Yeah, often this is going
it is growing during short phase, it will be decaying again. So it's not certain where you will have that point.
Fair enough.
No.
John, what?
So these are done with the gyrokinetic equation.
Yes.
How important do you think that is, as opposed to trying to capture the essence with a fluid type model?
I mean, for instance, this gyrofluid model, for instance, that Bill was describing with Griffin, I think could be quite useful. I mean, I don't see a priori anything in this flow shear physics which is going to be any more difficult to model with the fluid model than the usual kinetic issues of ITG and so forth. But I mean, I think it needs to be a nonlinear fluid model, but
I mean, the reason I ask the question is, I mean, the general topic of subcritical turbulence is very interesting, and you're much more likely to be able to do something analytically with a fluid model than the full
Sure.
nonlinear.
which is exactly what Sarah and Steve and Nunu were doing successfully, it looks like, at least qualitatively.
Okay, well, shall we pass the
Yes.
microphone?
And stick.
Hand it back over here.
Can you hear me? At the back? I guess so. Okay, so the idea now is actually using some of the features that we have seen in these simulations and use them to analyze possible bifurcations to enhance transport. So what I'm going to do is actually use a very simplified model to consider the different possibilities that we have to see in which parameter space we'll have bifurcations. So this is a very simple model which is meant to represent a tokamak that is heated by neutral beams. So I'm taking a flat surface, represented here, that contains in it all the volume in which the beam momentum energy are deposited. So once I look at in a steady state, all that energy and that momentum has to be coming through my flat surface, and that basically determines what my pi, my transport momentum, and my q, my transport of energy, is. And then I also consider that if I write the amount of momentum and the amount of energy that is coming with the beam as just a flow of momentum of a monoenergetic beam and the flux of energy of a monoenergetic beam again, and I divide one by the other, I see that the pi over q roughly goes like the major radius where I inject divided by the velocity of the particles of the beam. So that's something that is determined, it's given to me. If I have a beam with some technology that has some energy, then this pi over q is going to be a constant for me. So what I'm going to do is actually study systems in which I'm going to have some pi over q and some q and try to find steady-state solutions and see if I can find bifurcations. So just the final result is going to be the following. I'm going to be able to find two bifurcations in this system. The first one is by adding neoclassical theory. It's going to look very nice, but it's going to contradict part of the phenomenology. So let me get there and I'll explain how it is. But this one at least is robust. I mean, it's a robust phenomenon, and this bifurcation should exist in a tokamak. The other possible bifurcation is adding intrinsic rotation into the system, and this is much more speculative, and I'll get to that at the end. The idea of going to this one is because the neoclassical one somehow contradicts the phenomenology of transitions to enhance transport. So I'm going to show what the main, how I work this out with the simple example of balance without non-neoclassical, just the turbulent flows that we have. And what I'm going to do is use a plane in which I have the rotation, the shear of the rotation, and I have the temperature gradient. And I'm going to plot in it the curves that have constant Q and constant pi over Q. It's really simple. And then when I have these curves, I'm going to see where they intersect, and those are my solutions. So for the red lines here, I hope you see they are red. Those are the Q equal constant, but this is turbulent Q at this point, only the turbulent transport. And these are based basically on what Michael was showing. It has a maximum temperature. That has to do with the fact that as I increase, Michael showed this, the shear flow, I'm quenching the turbulence, and by the same Q I have, I get more efficient and I get more temperature gradient out of it. But eventually, I hit into this region of turbulence driven by the flow shear, and then my temperature gradient decreases, and I lose all the advantages. So these are my curves. In the dashed line, I plot a special curve, which is actually one of turbulent heat flow equal to 0, which is the critical gradient. And as you see, the critical gradient has this kind of dependence. I have an initial critical gradient, the ITG1 without shear flow. That critical gradient grows up to the point where I again find this PVG turbulence and it decreases. If now I include the pi over Q lines, and for this I'm going to use this fact that Michael was talking about, that you have the turbulent Planck number is actually almost a constant, I find that these lines are just simple straight lines that go through the origin. So if I just look at for the origin here, is below, this would be just straight lines that go through there. And that's basically just meaning that because the beam is inputting as much momentum as energy, I'm increasing the temperature gradient and the velocity at the same time, the velocity shear at the same time. So these are the kind of lines. Well, as you can see, they only intersect in one point. There is only one solution for a given Q and a given pi over Q. There is no bifurcation possible here. I have my solution, I cannot jump to another solution. And this comes from the fact that these lines, actually the Q constant lines, have a slope that is smaller than these very straight pi over Q lines, which are determined by the physics of my beam. These are these lines. So we cannot find any transition here. So what we did is actually, well, let's see what happens if we add neoclassical. Right? Let me begin now. Yes?
So those curves on the previous are an interpretation of the set of runs that Michael showed.
Exactly.
Finite magnetic shear or zero magnetic shear?
Well, if you have, that's a good question, thank you. If with the finite magnetic shear, it looks like this, right? If you put zero magnetic shear, what you get is that this gets very peaked. These lines get very peaked. So the Q constant lines are actually very peaked now, instead of having this smooth form, and the same with the critical gradient. But again, we saw it comes back the Q, so it's not, still have the same shape. So including neoclassical, let me describe the two types of curves. The curve that is a Q equal constant, and the curve is pi over Q equal constant. For the Q equal constant, if I envelop the critical gradient, again in that dashed line, I have that the Q equal constant lines are given just by neoclassical, and I'm assuming that this neoclassical doesn't, I mean, it actually doesn't in high flow, depend on the velocity shear. So this line just horizontal straight lines. The Q is actually given just by temperature gradient, if you are below critical. If now I add the turbulent flows, this is what I find. When I'm far from neoclassical, I get the typical shape I was showing before with an increase in temperature gradient and then an increase. When I get close to this region in neoclassical, right, I have this kind of shape where my flows, my temperature gradient and the rotational shear just came into the region where I'm neoclassical, and it has this type of shape. I have exaggerated here in the classical effect, so you can see how these things are different from the critical gradient curve. Otherwise, it will be very similar. So now let's go to the pi over Q. That's actually the very interesting one. You're going to see that the fact that we have a constant Prandtl number is what gives us trouble in finding the transitions, the bifurcations. So when we include neoclassical, right, we have two regions in our graph. Below the critical gradient, my pi over q constant line is given by the neoclassical Prandtl number. It's again a straight line, okay, between the rotation and the temperature gradient. But now it's given by the neoclassical Prandtl number. While if I go far from neoclassical, I'm very turbulent, that slope is going to be given by the turbulent Prandtl number. The fact is that the typical turbulent Prandtl numbers that we have are actually of order 1, while the neoclassical is usually like 1/5, 1/10. And that has to do with the different physics in the transport of momentum and energy in neoclassical. In neoclassical, the energy is transported by banana orbits that cannot transport momentum. So the momentum transport in neoclassical is much smaller. You see that that means that for a given pi over q, because transport momentum is less efficient, I must have a lot of more rotation, more rotational shear. So my slope is smaller. So once I cross the critical gradient, I have to join to this turbulent pi over q curve, and I do that, and the system does that doing something like this. What it basically does, it follows the critical gradient curve until it reaches the turbulent pi over q constant curve. And it does so because the only place where turbulence and neoclassical can compete is close to the critical gradient. So that's why it follows it. And here again, I inserted neoclassical so you could see the shape, but I mean, if I put a real neoclassical value, it really follows pretty nicely the critical value curve. And well, if I increase pi over q, this is what I get. As I increase pi over q, I get an enhanced rotational shear as compared to the temperature gradient. So I have these two types of curves. Now, how do they intersect? Where are my solutions? Where do I get solutions? Well, if I weigh over neoclassical, I find the case I showed at the beginning, only one intersection. No bifurcation, I only have one solution, I cannot go anywhere else but there, or unstable. What if, instead of having such a high Q, I decrease the Q a little bit? This is what we find. We find three solutions. What we find is the one that is more or less turbulent, one intermediate one, and then this one, which is with, sorry, I actually should have pointed out. I'm going to look only in the region where I see the bifurcation. I'll talk about the rest of the regions later, but just to point out that I'm going to cut, I'm going to zoom into that region. That's why you see that dashed line there. You see the gamma E is not so high, and this is actually a critical gradient line. So once I'm there, I have three solutions, right? And I can jump from one to the other. That could be done by, I don't know, maybe this, when you have these rational surfaces coming in, they'll get you a push and you jump to their solutions. Who knows, right? The thing is that if I continue decreasing Q, going down these constant Q curves, I get to a point where I'm tangent and two of the solutions go to each other. Now, if I try to go further, I cannot have a continuous function of the temperature against Q, and I have just to jump to the neoclassical line. So that's a transition right there, right? By doing this, we can go from this branch. If I continue decreasing, suddenly I jump there, and then if I continue decreasing Q, I come down to the neoclassical. If I plot that in this kind of graph in which I have ignore this. This is because I have increased neoclassical to enormous levels. These are huge numbers, but too irrelevant. But if I have the energy flux against the temperature gradient, and this is a constant pi over q line, I have the neoclassical line, the turbulent part, and then as I decrease the q, I get to a point where I have a minimum q below which I cannot drop, and then I have to jump to the neoclassical solution. Okay? We have observed this. Actually, Edmund did observe this in doing simulations in the zero shear limit, which is probably the best case. I'll tell you later why it's important to have zero shear. But here is the same graph I sketched before. I have neoclassical here. This is turbulence, and you can see how the q against t prime is decreasing until it hits a minimum q, and then it has to jump. So this actually is a transition that is robust. It's actually observed if you run these simulations and try to draw these lines.
And what's the distance between A and B most dependent on?
That depends on how it depends on the gradient of your critical R over LT line. So it depends on how big this is. If it goes like that a lot, then you have a bigger jump. Because if you notice, this is a jump between two lines. This line, this is the neoclassical line, the turbulent line, and this is the neoclassical line, and then this is.
And physically, what determines that?
It's the different Planck number.
Linear mode to E cross B shear?
Yeah. How good at the shear at quenching the turbulence?
Okay. Could you go back a couple slides? You showed a bit forward.
Forward?
There. You showed Q versus
This one?
This one, yeah. So this is an anti-transport barrier. You're seeing a bifurcation.
Yeah. That's you made my exactly. You made a bifurcation by decreasing Q. That's what goes against phenomenology. Absolutely.
Or by increasing pi over Q.
No.
Careful there. Well.
But this might call into question why the assumptions you've made. This only contradicts phenomenology if you assume that all observed transport barriers are always in quasi-steady state. I mean, you can decrease Q by, for some reason, temporarily storing energy inside some surface.
No. Careful here. It goes like this goes against phenomenology by something very simple. There is a power threshold for ITVs, and this doesn't have a power threshold. It has the opposite.
As an anti-power.
Actually, exactly. I mean, why would you want ITV if you are in neoclassical?
Well, but you can also, Felix, you can also get this transition by keeping Q constant and increasing pi.
Felix, that's not a question. If you go to my graphs, you look forwards, the ones I showed. If you go that one, yeah. So if you look at the green line, which is the closest to the neoclassical and the IT and the turbulent lines, there's no actual transition there because and that's a sort of lower Q. I don't know if this is something you already thought.
I know why this happens. I know why there is transition times and sometimes there aren't.
But there isn't a transition. You can go to too low Q and then there isn't a transition either.
Well, but then I mean the thing is, so this one actually is lower pi over Q, right?
Yeah, but it's also lower Q.
No. Q is this, right?
Yeah.
So if you are this pi over Q, you decrease. That's it.
Yeah.
That is no. I mean, this actually go. I'm not saying that this is not a transition. It's maybe we have to do something else to do this. I mean, maybe something else could save this transition. As it looks like now in a 0D model, which I mean the caveat of this is totally 0D. I have no profile considerations, nothing like no Coriolis pinch, nothing, right? So it could be finally that this is actually a transition. It's just that as it stands right now, it actually looks like goes against the power threshold.
But I mean, yeah, it's a lower value of pi over Q, but on that plan, each point is uniquely mapped by a value of, by a value of pi over Q. I mean, the region where that green line isn't accessible.
No, it is. It's neoclassical. It is neoclassical. If I have a lower Q, if I have that curve, and I go lower, it's neoclassical. I go neoclassical. So this pi over Q line is like this. It's like I showed before.
Oh yeah, of course. Yeah, sorry.
So if you go below that Q, you go here.
Sure.
So why do you want ITV if you have already neoclassical?
Sorry,
so that's the.
Sorry.
Well, I mean the thing is that this actually gives you bifurcation. It might be the important one because from what Peter has told me at some point, the value like the turbulent transport and the neoclassical transport are not that far when you get to an ITV. So it could be, but we need to study it better. So I'm not discarding it. It just looks against.
And how exaggerated? You said a couple of times that you've exaggerated the neoclassical transport level. How does it affect this kind of figure?
It affects, yes, it affects a lot. Like you see there is a big jump here from R over LT of 8 to R over LT of 13 almost. And in my case, it was very small. You see this is a very small jump. So the more neoclassical you put, the worse the jump decreases.
This is the exaggerated one you're saying?
This is the exaggerated one, exactly.
So going back, are you saying the other one is a realistic ratio?
It's a realistic ratio,
for
yeah.
some value of...
This is for the cyclone-based case.
But I think you also have to specify something more.
The new star, you mean?
Yeah. And
So,
is it typical of jet or compass D?
which one did you choose?
New star here is 0.01.
It's more like jet.
Yeah. So, a bit more collisional than jet.
It's small, what you said.
Yeah.
Okay, so, but it has, I mean, even though it has this big disadvantage that it seems to preclude like a power threshold, it does have a nice features. It actually tries to choose regions where you have low magnetic shear, and it doesn't like to be at a low power Q. So let me, oh, Jesus, 10 minutes. So let me show you the curves. Here the blue curves are the ones that I was showing before, the ones that you have a transition, you have several solutions for one Q. But if you go to a small, this pi over Q is increasing in this direction. If you go to a smaller pi over Q, you get that there is no transition, there is a smooth joint to neoclassical. And the same up here. If you go down this way, you lose that nice property. We have several solutions, and I'm going to explain you now why this is.
Can you tell us the sign again? Is it large pi over Q or small pi over Q?
You have to have high enough pi over Q, and you have to. And the other thing is you need to quench the turbulence well, like your critical gradient. I have
So
it.
it's more like neutral beams.
You need neutral beams, and you need to be at low magnetic shear, and I'll show that now. Well, and this is the idea. I mean, if these are my pi over Q lines, this is the critical gradient line, and what happened before is that there is a region, specific region of the pi over Q curve, this one, that is that gradient, that slope that is going to determine if we have or not a transition. If this becomes bigger, I can have several intersections. If this becomes smaller, I don't have as many. I don't have many intersections, only one. And as I decrease Q, you see, I smoothly go into neoclassical. No transition, no bifurcation in here. So the slope of this line, of this part of the line of pi over Q, that's what determines if you have or not transitions. And going back to the plots, you can see that it depends on two things. The first obvious one is the gradient of the slope of the critical gradient curve, which is how efficiently you quench the turbulence, right? That is, because this part of the curve pi over Q follows the critical gradient, if you change the slope of that line, you are changing the slope of the pi over Q line. So you want, sorry, I saw this incorrect, it's bigger, it's larger, pi over Q. So you want to come to this region here. You want to come to this region where you have bigger slope. And that actually favors low magnetic shear, because as I said, low magnetic shear has this structure more peaked. So you have a bigger gradient, you have a transition where before you didn't have it. The other parameter is pi over Q. The pi over Q, again, this is wrong, this should be larger. The pi over Q, as you come this way, you can see that these two lines, the line of neoclassical and the turbulent line, try to align with each other, so you lose this feature. So as you get to a smaller pi over Q, you lose that slope, you can lose the bifurcation. So this actually has two nice properties. You need beams. We saw this morning that you have a better ITB if you have beams. And the other thing is that you favor the regions with low magnetic shear. And that's actually the two, this is the low pi over Q, and that's where I'm getting into the maximum of the maximum critical temperature gradient, where I again lose the transition. This next slide was to actually explain why some lines intersect, but that's not so important. So this is the neoclassical bifurcation.
Can you go back to one of the bifurcation figures? I have a question.
Sure.
Say that one. The normalization has a temperature. So if the temperature changes by a factor of 4, the heat actually goes down.
Yeah.
Pi doesn't. So I think that or maybe
No.
the normalization of pi does. But anyway, Q changes quite a bit.
Yes. I know that. Is one of that's one of the effects. I cannot.
Does that make it fit with the phenomenology better?
No, it should fit in 0D too.
Yeah, I think so. It's difficult. I mean, it could be that in 1D it fits, but I don't know. Okay, so these are these neoclassical bifurcation advantages, right? This happens because the Planck number of neoclassical transport is smaller. It's actually numerically tested. We have seen that the cyclone-based case does have it, so it's robust. It's possible to take large jumps from RLT of 8 to RLT of 12, 13, so it's okay. It favors neutral beams and low magnetic shear, which is okay. This is the problem. It is easier at lower powers, so it does seem to go.
Higher temperature.
Or higher temperature, yes. Yes. So that's what lets us to go to and just totally go crazy and suggest some out there idea, which is actually including intrinsic rotation. Why do I call this intrinsic rotation? Well, when we are doing flux tube simulations, we're actually making an expansion in the size of the gyro radius, in particular the size of the poloidal armor radius. So if we get the next order terms in that expansion, apart from the part of the viscosity we already have, we have terms that are small by rho poloidal and had second derivatives of the rotation and the temperature. If we go to a low flow regime, this is actually stretching a little bit, but let's do it. This term can be cancelled, and you can actually obtain a relation between the transport momentum and the transport of energy, both in the turbulent neoclassical regimes, that has a constant Planck number, but has an extra term that depends on the second derivative of the temperature. If now I get this kind of equation and make that equal to 0 by saying that I don't have any momentum input, that will give me actually intrinsic rotation. That's why I call these intrinsic rotation terms. This drives intrinsic rotation by including these next order terms. And the model that describes this is actually published in 2010. Well, the idea is now that if I want to use this in a 0D model, I need to say how big is the second derivative term. And because it's divided by a first derivative, it's just this kind of RLT. The sign is indeterminate. And if I have actually a big structure, like a big ITB or like a shear layer, I have both signs. So I can choose whichever of the two I want. And now what I'm going to show is what, as again, I repeat, I said before, the pi over q lines seems to be the difficult ones to drive towards a transition. So what I did is actually redraw those with this new term included and see what happens. And I'm going to show two cases. You see there are two alpha parameters that decide one for turbulent and one for neoclassical. And depending on the sign they have respective to each other, it means that intrinsic rotation driven by neoclassical could have the same or different sign that intrinsic rotation driven by turbulence. This sign could change from neoclassical to turbulent. So what I did is look at both possibilities, and this is one of them. If I have both of the signs equal, that means that both neoclassical and turbulence are driving towards the same, are driving intrinsic rotation in the same direction. Here I have again T prime against omega prime, and then I have like the critical gradient curve. We have now, because intrinsic rotation is helping rotation, we have that instead of having the straight lines we had before, now as for a constant pi over q, I get gradually more and more and more shear, rotation shear, than actually get temperature gradient. So much so that in this extreme case, I look for an extreme case, I never get to touch the critical gradient line. There are actually a turbulent equivalent, but because I don't get to touch the two lines, they are separated, like they are disjoint curves. And they actually have this really nice shape in which there is like a pi over q is increasing this way. There are close curves. And this again, if you look at the shape of these curves, it is again the same thing. This rotation is helping the momentum and is getting a lot of velocity here. If I have the two neoclassical and turbulent go opposite ways, it happens the opposite. Neoclassical now is being, the intrinsic rotation goes against momentum, and the curves turn the other way. They now connect to the turbulent ones, and again here you see this gentle sliding going towards more and more gamma e, but this is slower because it's not being helped by this effect, the sign of this. If we use the other case, which is the one that is going to work out really nicely, this is what I get. These are the typical. I chose a one pi over q, one in particular, and if I increase the q, I go from neoclassical, then I become turbulent with two solutions now. And if I push hard enough, I get to the tangency, and over that, I bifurcate because I don't have any other solution. So this one, ignore this region below here. This could be actually problematic, but it's because I exaggerated the effect of initial rotation. You could jump and get to another bifurcated state. And if I plot that in a q against t prime graph, this is what we get. Again, there is for every pi over q, there is a maximum q over which I have to jump to neoclassical. Neoclassical is this line below, which, as I said before, is totally disjoint from the lines above. So if I cannot get a solution here, I just jump to neoclassical in this simple model. So this is very speculative. It turns out that it has a big effect, even though this term, the rho-poloidal, is supposed to be small. It surprisingly has a big effect, yet you still require high energy input, pretty high. So it's not the most convenient one. But there is a power threshold, not like the other one.
Do you mean VB or Q when you say high energy input?
Q. I'm talking about Q. You see, these are like 70 or something like that. And this pi over q, in fact, is 0.2. This one here, which is the preferred one, is not so far from experiments. Experiments are 0.1 in the normalized units we're using in these graphs. So this is twice what a beam is doing right now for momentum input. And what we were talking before, it was in the graph before 50 or 60 was actually the cyclone base case, which is pretty exaggerated heat flow, right?
It's already exaggerated.
Yeah, so it's down there, yeah. So, and that's it for my part. So we continue or just?
So you say you need 5 more minutes?
Well, I don't need it. If we want 5 more minutes, I could.
Why don't we handle the questions first?
So, I didn't quite get your last point. So where is the experiment in your graph? Where are the real values?
So
Q is quite low, you say.
It's a pi over q. Is so further usually, I mean, the biggest pi over q's you can get, I think, 0.1 in the normalized units I'm using here. So that's, I don't know, I think it's this one or this one of these.
Q over Q jar bone in experiments is tiny.
It's below
10, right? It's actually.
But then you've exaggerated intrinsic rotation in this figure, right?
And yeah.
Not this one?
Actually, yeah, it's complicated because it depends a lot. These graphs depend a lot actually on how much initial rotation I put into neoclassical and how much I put into turbulence. And this one have a lot of neoclassical initial rotation. That's why I think I'm going wrong, and that's why I don't reconnect to the point below. Actually, the rho-poloidal I'm using is 10 to the minus 2 as compared to the size of the device. So it's a normal rho-poloidal.
Compare that to experimental values, the shots that I showed where you saw the strong barrier forming that had a Q over Q gyrobulb of about 5.
So it's very low here.
R over LT of about just below 10 when it starts forming. And then when the ITB forms, it shoots to 25 or so.
So is your Q gyrobulb the same as this Q gyrobulb?
These ones, I'm using the ones that in which the results were presented, and those normalized to big R, to the major radius.
Remember, this is cyclone-based case.
Yeah. The question is the denominator in row star R or LT? And I think it's different in the two cases.
Yeah, I think you probably are using the minor radius, right?
No, we used LT.
Yeah.
LT. Okay.
Just to say, the cyclone-based case has 50 times more heat flux in the real experiment.
Yeah.
So it's way off.
No, I agree.
So you should view this picture topologically rather than.
I mean, the idea here is trying to include terms that get the curves. I mean, there are many terms in that. There's only second derivatives. There are multiplications of first derivative of temperature. density derivative with respect to temperature derivative. In turbulence, I have no idea. I don't think anyone has actually calculated them. For neoclassical, I know there is Peter has calculated the ones for Fierschluter, and I know there is in base aspect ratio expansion, we have the banana regime ones, but I don't remember the sign. The important thing though to remember is that if you take the second derivative ones in particular, there you have both signs in the second derivative. If you have a strong structure, the second derivative has both signs. So that's why I choose this one, because I don't have to depend on the sign of these alphas. Only the ratio between them two. If the sign changes one with respect to the other.
But are you saying that any of these terms any gradient terms, linear, products of linear or second derivatives in density will all have the same behavior?
Not all of them, no. I mean, this is the...
This one you picked because it was temperature, because you were doing heat fluxes, temperature.
Yeah.
Neoclassical as well. That way you focused on the ion temperature.
Ion temperature. I could have actually put a term here that has the temperature derivative to the square.
Yeah.
And will be the same kind of scale. But in that one I have to choose a sign. That's my problem. In that one I have to choose a sign. I need to know which alpha sign I have, but with the second derivative I don't.
Right. Okay.
So.
Okay. Anyone else have any questions? Okay. So I think the last bit of it is Michael was going to say.
I can say
just a couple of
just
words
a few words, I guess.
about Trinity, right? So and then we'll aim to finish it. In fact, we'll aim to finish early. It's the advantage of having double acts, right?
Okay, so I really don't want to keep you much longer. I'm just going to say a couple of words about kind of where we plan on heading in the future. So, I mean, Felix was alluding to the fact that this is a 0D model. There can be more effects that can come into play whenever you're looking at 1D models. And this might change the picture somewhat. So, ultimately what we're going to do is we're wanting to predict the mean profiles. And of course, we've seen that shear, Q values, and so forth play a large role both in the experimental talks and from what the results that we were showing numerically. So of course, we want to consider radially varying magnetic geometry. We also want to look at things in the 1D profiles like Coriolis pinch. There are local terms which we haven't been considering. A point that I think Ian was bringing up is that we're considering the heat flux to be the same as the power input, for instance. When in fact it doesn't have to be the case. If you have some sort of local heating, then this balance isn't correct. So there's some things that can change the picture. So you have local turbulent viscous heating, temperature equilibration, and so forth. And so we'd like to do the inverse problem, which is let's specify heat fluxes and momentum fluxes, and let's get density and temperature gradients and flow gradients. And this is a more forgiving problem in some ways. It's very challenging, but at the same time, this stiffness that we see, the sensitive dependence of the heat fluxes on the temperature gradients, goes away, and in fact we have the opposite effect whenever we try to solve the inverse problem. Because if you get the heat fluxes off or the momentum fluxes off by some amount, then it's much easier to get the correct temperature gradients and the flow gradients, even if you have the fluxes off by some amount. So we want to look at that kind of problem. In order to do this, we really need to look at how the turbulence couples to the mean profiles, and that's complicated because the mean profiles have scales which are on the same size, both in space and time. So meters is the scale size. In space and in time, it's seconds. Whereas we know that the turbulence is much faster and is on much smaller scales, micron scales and could be up to megahertz scales. So it's not really possible to do a direct numerical simulation for a device like ITER where you look at the smallest scales of the whole device and for the whole discharge. So we'd like to break it up. And so in the end, if you do the sort of analysis that Steve was alluding to in his opening talk, you take gyrokinetics and apply that gyrokinetic ordering to the full kinetic equation. You expand, you take advantage of the fact that there's a scale separation between these equilibrium space-time scales and the turbulent space-time scales. Then you get not only the gyrokinetic equation we've been using, but also at higher order you can take moments and get these closed set of equations for the evolution of the mean, density, pressure, and toroidal angular momentum. And I'm not going to say much about this. I just want to point out that these depend on these fluxes of the particle flux, the heat flux, the momentum flux, which we've been talking about earlier today. And these are going to be space-time average versions, space-time average over the turbulence scales. So this is an equation which has only mean, time, and space scales in it, so it's easier to solve than coupling all the time and space scales into one equation. And so we're just going to do this using a multi-scale algorithm where we solve for the turbulence in small regions here in space and time. So we're looking at temperature profile versus radius and time. We're going to look at small regions where you have a fine scale mesh for the turbulence, and we're going to embed this in a coarse grid where we're going to be evolving the mean profiles. So a 1D radial grid for the mean profiles. And each of these little regions in which we're going to be resolving the turbulence is represented by a flux tube simulation domain, which is shown here. The flux tube simulation domain follows around the magnetic field line as it wraps around the device. And so this has been implemented in a code called Trinity, which you've heard alluded to a couple times this week. I won't go into too many details. Basically, we just sample the radius, sample the temperature profile radially, each radial grid point representing a flux surface, which is represented by a flux tube. And because these transport equations are stiff, they have sensitive dependencies, the heat fluxes depend sensitively on the temperature gradients, we have to use an implicit treatment. We use a Newton's method. I don't want to go into the details. The idea is that because we do this, we're allowed to take time steps which are much larger than we'd be allowed to take otherwise. So we can take time steps on the order of tenths of seconds, which is closer to the energy confinement time, instead of time steps on the sort of turbulence simulation takes about it should run for about a millisecond. So we save something like a factor of 100 in the time domain. And so just one example piece of data I'll show. This is taken from a jet shot. It's a meteor demonstration discharge, which is with deuterium and tritium, and at the time it's a record fusion energy yield. And so these are the kind of results that one can get from Trinity. These are the first results that we got, showing the red and the blue lines are the ion and electron temperature profiles from Trinity, the black being the density, and these dotted lines and the points here are the experimental data. So all I want to show is that these give relatively good results, which agree to within 15% across the device all the way out to 0.8 here. And as we saw earlier with this week, with the talks from the D3D crowd, we see that not only do we want to look at mean profiles, we can also then compare fluctuation measurements for things like density, ion electron temperature, and potential measurements with experiment. Here we have it because these diagnostics were not present for this shot, but it's something to look at in the future. So that's it. In the future, what we're going to be doing is looking at how these rotation profiles are going to be evolving in time using this self-consistent 1D model Trinity coupled to these gyrokinetic flux tube codes. And I won't go on and on about the conclusions. You've already heard us say them pretty much. But so this is what we're looking at doing. And I think it'd be very exciting because these simulations are going to be very expensive to look at what, for instance, John mentioned and Bill mentioned yesterday, looking at something like coupling Trinity to something, gyrofluid, nonlinear gyrofluid codes, something where you can actually do parameter scans very quickly and look at new confinement concepts. So, thank you very much.
Okay, well, we have some time before the tea is ready, so please ask questions, and if you want to ask questions of previous speakers, please feel free to do that as well. Peter.
These profiles that you showed, did you match them at the edge?
I matched them at the edge. Yeah. It's not necessarily like T-gyro. I think T-gyro has the option to match them anywhere across the profile, but we only match them at the edge.
The heat deposition.
And the heat deposition was taken from the experiment from transp output, essentially.
Including alpha particle heating?
Including alpha particle. Well, alpha particle heating was calculated from a database, essentially.
Right. So in which way would you like to include the toroidal momentum transport?
In which what?
The toroidal momentum transport.
What about it?
You also have a new transport equation, and,
yes.
And you also get the results from the flux tube simulations.
Yes, so that would be
just everything.
Yes, so that's the idea is just to run. So in this case, we didn't have the momentum transport equations implemented here, so we were only evolving density and the temperature profiles. But yes, the idea is to then also couple to this momentum transport equation, which I had up here a moment ago, and get the momentum fluxes like we saw before from the gyrokinetic.
So no models?
No models. I mean, the simplest model probably to test with is this model that we were using to get these bifurcation curves. So assume the Prandtl number is just a number, and you find Q and you can get pi that way, for instance, using some reduced model for Q.
The current profile is given.
What?
You do not evolve the current profile.
The current, no, we're not. I mean, there is sort of an effort in the works right now to start solving the Graf-Shapronov as well and evolving magnetic geometry, but we aren't doing that currently.
Yes. When you are doing flux tube simulation for rotating plasmas, you also rotate the flux tube domain numerically. So such a kind of technique are required for.
I'm sorry, you're rotating the flux tube simulation domain in which sense?
I mean, so fluctuation tend to localize around the KR vanish shear, right?
Yeah.
So in that case, I suppose eigenfunction or flux structure is also rotating horizontally.
Yes, that's right.
So in order to do nonlinear simulation in flux tube simulation, you have to. I wonder if you have to.
You typically have to go to high resolution. It's more expensive to do flux tube simulations usually with the rotational shear because, as you say, you go to higher and higher mode numbers in KX. You have to hire because KX is evolving in time to take care of what you're talking about, right? So we have to go to usually many more KX in our simulation than we would normally to resolve the turbulence.
I don't know, maybe I've already implemented, but Coriolis pinch effect was implemented and used by Clement and Jones. So maybe.
So it would be definitely be nice to speak to him. I mean, it's not in the main development version of the code. So it would be nice to actually communicate with him. And I do remember seeing a paper in which he had implemented the Coriolis, but the results we're showing didn't have the Coriolis term.
Yeah, maybe in an old version, I don't know, but
sure.
Maybe you can take over some.
No, that would be nice. Yeah.
Jeff, probably required to sort of follow. What happens as you approach a bifurcation in Trinity?
Well, we haven't seen one yet, so we can't say for sure. So there are a couple of things that there are a couple of options.
No, presumably jump to the turbines would shut off and it would continue to heat up until neoclassical or something else.
And you should
exactly.
your time step is adjustable.
And so my time step is adjustable. So it may be the case that, yes, it starts to steepen, the time step has to start decreasing considerably. And it may be that, in fact, the gradient increases drastically to a neoclassical level, in which case maybe the width of it goes out of the gyrokinetic ordering. And so we may not be able to say anything, it's unclear about the saturation of the transport barrier. But what we really want to be able to see is at least the onset of the transport barrier.
Do you do the neoclassical transport as well? Or is that
We do. I mean, right now we have a simple analytic model for the neoclassical transport, Chang-Hinton. But there are. It's been a long process of inactivity. But there's an attempt right now to couple with NEO, the solver of Emily Belly and Jeff Candy, which is a much more advanced solution for the fluxes.
Anyone else? Yes.
Yeah. I guess I want to go back to that issue I brought up earlier about the magnetic shear versus your E cross B shear. Were you? I think you weren't assuming anything special at the value of Q, or you were taking Q from this.
It was just the base case, Q of 1.4.
I'm just trying to connect that with like what Peter showed this morning. Experimentally, we see that low order rationals have some kind of magic with that. And you see everything.
I mean, so we're not looking at low order rationals here. It's hard to say, but my understanding from Peter's talk is that low order rationals might have an effect in triggering and kind of giving the system a kick and putting it into a transport barrier regime, but then you still need the rotational shear to get it to work. So what we were really trying to ask here was, do we really need these low order rational surfaces, or are those just something that kind of give us an extra little kick and help the rotational shear? So our question was, can we get it with the rotational shear and not worry about the low order rational surfaces?
Greg, my understanding is perhaps out of date. So my understanding from D3D, and I thought Judd, was that low order rational surfaces might give you a lower power threshold, but even without low order rational surfaces, you can still get an ITB. It just might require a higher power threshold. Is that not true on Judd? Do you always need a rational Q?
Yet we need some kind of trigger.
But for example,
when you say some kind, is it always
well,
rational
like you
Q?
have, like for example, with the optimized shear, there's a different trigger mechanism in play, which I didn't discuss.
But it doesn't have to be the rational system.
So it doesn't have to be the lower order rational.
In that case, it's not a low order rational.
What is it?
We see some kind of mode activity at the edge, and we wonder if that's coupling into the core. Some like mode, like a brief lock mode appearing when we reach a Q edge of an integer at the edge of the plasma.
So this could be like Zonka's idea that that kind of long wavelength, typically alphanic activity that we normally wouldn't think would come from turbulence might start a zonal flow there, which kicks off the whole barriers.